All right, so I'm going to give you a quick overview of how I think you ought to collect your data for this Ohm's Law lab. Um, First of all, you're going to be going to the simulator to create the circuit, and you want to match the circuit that is here. So you've got a battery, you've got a resistor, and you've got an ammeter all in series. So we'll say here's the battery. We'll grab some wire, go boom, boom, boom. Let's say we want our resistor there, and then we want to come down here and have a little place for our ammeter, and we'll finish it up and close the circuit. Okay, we've got the current flowing, hunky-dory. Now, if you want to adjust things, if you click this little slider deal, you get a magnifying glass. And so you can change the values of your battery, the number of volts the battery is producing, the number of ohms that the resistor has, and you can vary the, or actually just can read the current in amps here. So you have to figure out what are you going to use for your values. In the first, you're going to be doing two experiments. The first one, you're going to have a fixed resistance. So let's see what the resistance value is here. It's at 10 ohms. I'm going to do just some weird number so that my numbers are not the same as what yours will probably be. So we're going to say our resistor is going to have 13 ohms. And let's say we want for the value of the voltage, let's do some weird, let's do 26 volts. Okay, it's probably a lot more than you would normally do, but whatever. Okay, so we're not going to change our resistor. We're going to be changing our voltage, and we're going to read the current that results from the changing voltage. So this is the dependent variable, and the voltage would be the independent variable in this circumstance. All right, so let's pause this for a sec, and we'll go over to open up a blank, sorry about that little break. We're going to open a blank spreadsheet, and we're going to make three columns. Volts, or voltage in volts. Let's see, I will actually call this voltage, because that's what we're measuring. In volts, current in amps, and resistance in ohms. So in order to make an omega symbol, which is what that little horseshoe is, I just Googled omega symbol and copied it off of a web page. There are shortcuts that you can learn, but I can't remember what they are, so this is what I did. All right, so you're going to be changing your voltage, and you're going to be reading the current that results with a fixed resistance. And so I basically put these all in the same table, and I'll show you how I'm going to be collecting my data. So in preparation for taking the data, since the voltage is something that we're going to be controlling, I decided to just make it easy on myself and make it 2 volts difference between each reading. So start off at 26 volts, then at 24, 22, 20, and then we'll just read off what the amperage is. And also, since we're going to be keeping the resistance constant, I'll just copy that and paste it down here so that that's always the same. All right, so let's go in and just make the measurements, make these changes. So here, if I reduce the voltage by 2 volts, now we come up with 1.8. Okay, so 1.8. Reduce it 2 more to 22, that's 1.7. Reduce it to 2 more, 1.5, and so on. So I put all the data in. Turns out that this will not allow me to go to 0 volts. So my lowest voltage turns out to be 1 volt. All right, so now I've got this table, and I'm going to take this and I'm going to copy this information here. And I'm going to open up Desmos and paste that into Desmos so that we can graph it. So here we are with the blank Desmos sheet. I've copied those 2 columns and I'll paste them in here. And look at that. It looks like a pretty nice, clearly it's not a parabola. It looks very much like it's a linear relationship. So let's see. If you remember the formula for a line, y equals mx plus b, where m is the slope and b is the y-intercept. So Desmos equation is y1 is about, that's what the tilde means, mx1 plus b. Okay, and that looks like a really nice nice line of, it looks like it fits quite well. Let's see if we can get the colors to match up. I'd like to make them all, that's better to me. Indulging my OCD. So they're off by a little bit. Some of them are above the line, some of them are below the line. That's probably because the precision with which we are able to measure the amperage is down to just 1/10 of an amp. These are probably not exactly 0.10 or 0.20 or 0.30, and that's probably what's giving us that little variation. But it looks like a pretty darn good fit. 0.998 is our squared value, which means that it's an excellent fit. And the value for the slope, which is one of the things we'll be interested in, is 0.075. So let's remember that. We forgot to put in our axes labels. So volts, voltage, parentheses, volts. And the y-axis is current, parentheses, amps. Right? And we could probably do a little bit better with scaling everything, but that's not too bad. I might as well get really obsessive about it. The maximum voltage is 26, so let's go up to 30. Okay. And the maximum amperage is 2 amps. And the maximum current is 2 amps. So let's go from negative something, negative half, give or take, to maybe 2.5. Okay. And now that's pretty much using the big area, so we're not wasting any space. It's easy to see that it's a really clean linear relationship. So let's record our data and then go to the second part of the data collection. So let's go down to the second part, key question part 2. How does changing the resistance affect the current in a circuit? So it's affecting the current, so the current is still going to be the dependent variable. The voltage is going to be our constant, and the resistance is going to be our independent variable. So we're going to be changing the resistance at a constant voltage and seeing what that does to the current. So let's go back and set up a spreadsheet to capture that data again, and we'll go from there. So I have set up a spreadsheet similarly to how I had done it before. Again, this is going to be a constant, so let's just keep the voltage the same. And I just chose these numbers at random. Voltage 35 volts, why not? Whatever. And the resistance, again, I cannot put the resistance on the simulator to 0. So I put the lowest value that it would allow me, which is 1. And then I just increased it basically 5, 10, 15, 20, 25, 30, 35 ohms. And so let's go and see what the information, what data comes out when we measure the amps at each of these resistance values. All right, so I've put in 35 volts, 1 ohm, and it's not too happy with me. It's blinking, so I probably should change it. The value is 35 amps, so I will put in 35 amps there. Let's change this now to 5. All right, it's a little less angry with me. And the amperage now is 7 amps. All right. So at 10 ohms, whoops. All right, at 10 ohms, it looks like it's 3.5 amps. And at 15, it looks like 2.3. And so on. And so that is what we read. And let's just copy our data off of the spreadsheet here. And we'll open up Desmos and we will graph that. So we'll paste those two columns here in Desmos. This is a very different looking graph. We might want to actually get a couple more data points in here, but maybe not. Let's see. So what does this look like? What shape does this set of dots look like it's making? Any thoughts? Well, it looks to me like it's a hyperbolic curve. And the relationship, the formula that is a hyperbolic curve is an inverse relationship. So y value, so y1 tilde let's use a different value. So let's say n divided by x1. And that looks like it fits quite nicely. All right. Clearly, we can ignore the negative values here, but let's make that a little bit nicer. Let's change the color so that it's the same. Good. Now let's change them both so that they're purple. Why not? All right. So once again, we want to scale our graph and label the axes. So the x values are resistance and ohms. Well, I can't remember how to make that, so I'll just spell it out. And the y value remains current amps. All right. And I think it's scaled pretty decently. Good enough for right now. All right. So that is, let's look at the Desmos values. So n, it looks like it's 35.001, which is pretty darn good. Oh, this is a almost perfect R value. So R squared is 1, which means that this is the ideal relationship mathematically that relates these different data points. So remember the n, so the value for that's in the numerator is 35. Let's see if we can figure out where that comes from.